Hello students, in this session we'll discuss how to design the superelevation and providing the radius of horizontal curve. We have learned in the previous session that when the vehicle negotiates the horizontal curves, the centrifugal force will be developed. The centrifugal force what is developed is counteracted by providing the superelevation. And we have also learned that the maximum amount of superelevation can be provided will be 7% and the minimum lateral friction should be 0.15 at the horizontal curves. So now using this we'll look how to design the superelevation value. In the first step, these design steps are given by the IRC guidelines. In the first step, the superelevation is calculated for 75% of the design speed. That is, we will have the design speed. If the design speed is 80 kmph, compute 75% of 85% and design the superelevation. Check what is the superelevation value that comes to you, neglecting the friction value here. So we need to consider F value as 0 and design speed as 75% of the design speed. Considering that, find out what is the value of superelevation. So now when you substitute V is equal to 0.75 V and F is equal to 0, we will get value of E as V square divided by 225 R. So using this expression, check the value of superelevation that we obtain. If this value of superelevation value obtained, if it is less than 7% or 0.07, the what value we obtain in the step 1, that will be provided as the superelevation value. If in case the superelevation obtained from the previous step exceeds 0.07, then the superelevation value has to be restricted to 0.07. So this indicates that providing the superelevation, it's not sufficient alone to counteract the centrifugal force. Then the friction lateral coefficient is also necessary to counteract the centrifugal force. Then in the next third step, by providing the maximum value of superelevation as 0.07, we need to check for the coefficient of friction developed. Okay, so now considering the equate now in the third step from the previous equation, superelevation expression, what we have, this is a superelevation expression. So in this expression, substitute E plus F is equal to V square by GR. So in this expression, substitute value of E as 0.07 because in the previous step we have considered, we have restricted the superelevation value to 0.07. So hence we are substituting the value of E is equal to 0.07 in the equation and we are finding out the what's the lateral friction value developed. So this value what is developed, that should have the value should be more than 0.15 because the minimum coefficient of friction required, lateral friction required at the horizontal curve is 0.15. Hence, in the third step, the friction what we obtained, that should be more than 0.15. If it is more than 0.15, then the what value we have designed, it is safe and design will be accepted. By chance the superelevation value is less than 0.15, so then what we have to do is either the radius of the horizontal curve has to be increased or the speed has to be restricted to the safe value. Then the design speed or the restricted speed will be calculated in the next step. In the restricted speed to calculate, we will consider the value of maximum superelevation value as 0.07 and F value as 0.15. So substitute the equation, these values in the expression E plus F divided by V square GR. So from this equation, we can find out substituting the value of E as 0.07 and F as 0.15, we will get VA will be equal to square root of 0.02 GR or if you convert the speed value, this will be equivalent to square root of 2.156. By substituting the value g as the 9.81, we can further reduce the restricted speed to square root of 2.156 r. So here the speed value will be in terms of meter per second. So if you want the speed value in terms of kmph, the same value we can convert the speed value to the kmph. By converting it, we have an expression VA is equal to 27.94 into square root of r. So whenever it is not possible for us to provide the superelevation and friction value as per the requirement, what we have to do is we have to provide the maximum allowable superelevation and the friction value, but the speed has to be restricted in such situation. So we'll look into some of the example and we'll see how the superelevations will be designed. So here you can see that two-lane load has to be designed for the speed value of 80 kmph and negotiating the horizontal curve of 480 meters. So we need to design the superelevation and also by considering the pavement width as 7.5 meter, we need to find out how much the outer edge of the pavement has raised with respect to the inner edge. So we have already learned that when the superelevation is provided, outer edge will be raised with respect to the inner edge. So that will be the rate of superelevation that is provided. So here they have given the width of the pavement as 7.5 meters and we need to determine what is the raise of pavement with respect to the horizontal. So now first we will design the superelevation. The data given as V is equal to 80 kmph, radius of curve will be 480 meters and pavement width is 7.5 meter. The first step will be to design the superelevation for 75% of the design field. That's the first step in the superelevation design and we need to neglect the friction. So by considering V as 0.75 into 80 kmph and F is equal to 0, we can find out the value of superelevation as 0.059. So here we can see that the obtained superelevation is less than 0.07. So hence what superelevation is obtained for the particular design speed and the radius of curve is acceptable. Since the value is less than 0.07, the superelevation of 0.059 is acceptable. Other we can say it as 1 in 17 may be adopted. In the second, we have to find out what is the raise of outer edge with respect to the inner edge. So now we know that the tan theta is equal to E divided by, at the small angles, tan theta will be approximately equal to sin theta. The sin theta is nothing but the opposite side divided by hypotenuse, that is E divided by B. Hence we know we have to find out what is the E value, capital E value. The small e value from the previous step we have obtained it as 0.59 and we know the pavement width is given as 7.5 and we can estimate what is the height of rise. So it says that the outer edge of the pavement has to be raised by an amount of 0.44 meter with respect to the inner edge. So in the second numerical, the example, it says that we need to design the rate of superelevation in the horizontal curve of radius 500 meter and the design speed is given as 100 kmph. So first write down the data that is given. V is equal to 100 kmph and R value is 500 meters. In the first step, we need to find out the required superelevation at 75% of the design field and neglecting this superelevation. So we have an expression E is equal to V square divided by 225R. It's a reduced equation for 75% design speed and neglecting the friction value. So now substitute the speed value and the radius value and find out what is the superelevation that we obtained. The superelevation what we have got from the calculation is 0.089. So here it is exceeding the maximum rate of superelevation of 7%, nothing but 0.07. Hence it is not possible for us to provide the superelevation value of 0.89. So in this condition what we have to do is we have to restrict the superelevation super elevation to the maximum value of 0.07. Adopt E is equal to 0.07. And in next step, check for the friction value. So what friction value provided we will obtain, is that sufficient to counteract the centrifugal force. So now for the coefficient, to check for the coefficient of friction, take the same equation, E plus F is equal to V square divided by 127 R, the super elevation equation. In this, substitute value of E as 0.07 and remaining all, you substitute all other data and find out what is the friction value that is obtained. So here obtained friction value is 0.087, which is less than 0.15. That's the maximum friction value, lateral friction value permissible at the horizontal curve. So now we can say that the design is safe. Though we restrict the super elevation for 0.07, the sufficient lateral friction is developed at the horizontal curve such that the centrifugal force can be counteracted and the vehicles are safe against the overturning and the lateral skidding. Therefore, we can say that the design will be safe at a super elevation of 0.07 and F value just 0.087 is sufficient to maintain the safe condition. So let us take the another example. It has given that the design speed of the highway is 80 km/h, horizontal curve radius is 200. We have to safe limit coefficient of friction is 0.15. What we have to do is calculate the super elevation to maintain this speed, and if the maximum super elevation is not achieved, calculate the allowable maximum speed of the horizontal curve. So now we'll go the step-by-step procedure for the super elevation design, taking the V value as 80 km/h and R as 200 meters, and we'll step by step check whether the requirement for E and F satisfies or not. In the first step, design the super elevation as per the 75% design period. Neglecting the super elevation, we have the expression. It's the same step as we followed in the previous example. So now we can see here that obtained super elevation value is greater than the maximum permissible super elevation value. Hence, we cannot accept the super elevation what we have calculated, and we need to restrict the super elevation value to 0.07. If we restrict the super elevation value to 0.07, then we need to find out what is the coefficient of friction developed. So now in the super elevation equation, substitute E as 0.007, that's the maximum permissible value, and find out what is the friction that is developed. So now you can see that the friction value what is developed will be, so there is some mistake with this problem. Result what we have got, the friction value developed will be 0.18. So here the friction value is exceeding the maximum amount of lateral friction that is to be considered at the horizontal curve. So hence it is not possible for us to provide a friction of 0.18. Then what we have to do is, we need to, here the friction developed and the super elevation what we are providing, that is not sufficient to counteract the centrifugal force. When these two conditions are failed, then what we have to do is, we have to restrict the speed of the vehicle. Now usually the design speed of at that horizontal curve is 80 km/h. So for the 80 km/h speed, when the vehicle travel at the 200 km/h, this value of super elevation E is equal to 0.07 and F is equal to 0.5 is not sufficient to counteract the centrifugal force. Thus what we are doing is, we are restricting the maximum speed. The speed value, we have to find out what is the maximum allowable speed. The maximum allowable speed can be calculated as square root of 27.94 R. So substitute value of R here and find out what is the restricted speed. So now you can see here that the design speed is 80 km/h, but the E and F values are not sufficient there, and that's why we are restricting the speed to the 70 points, say about, we can say it as, we will restrict the speed to 70 km/h at that horizontal curve. So this is how we have to check for the maximum super elevation and friction developed at the horizontal curve, and we have to decide whether the restricted speed is required or not at the horizontal curves. Once we decide the super elevation, we can check for the radius of the horizontal curves. Horizontal curves of highways are generally designed for the specified ruling design speed of the highways. However, if this is not possible to provide the horizontal curve for the ruling design speed due to some of the site restrictions, the horizontal curves may be designed considering the minimum design speed of the highway. If we consider any highways, we will have two speeds. One will be the ruling speed, another one is the maximum speed. So if I say for the NH, the speed limit will be between 280 to 100 kmph. So here 100 kmph will be the ruling speed and 80 kmph will be the minimum speed. So now when the horizontal curves are designed, the radius has to be designed for the ruling speed. But when the site restrictions are there, we can design for horizontal curve radius for the minimum speed. Now for the centrifugal force speed developed when the vehicle negotiates the horizontal curves of radius r at a speed of v kmph, and that will be counteracted by the super elevation E and the lateral friction developed F. So considering that, we have an expression E plus F is equal to V squared divided by ER. Okay, so by reducing this equation, we can find out what is the ruling speed. So if you substitute the speed value as ruling speed, then the radius of the horizontal curve computed will be R ruling. R ruling will be equal to V square divided by 127 E plus F. So whenever it is not possible to provide the ruling speed, then what we do is we will consider the minimum design speed V kmph, and we will find out the absolute minimum radius of horizontal curve or minimum, which can be given by V dash square. So here V dash is the minimum speed at that particular highway. Okay, like this we can find out the horizontal curve required, radius of the horizontal curve required. So if you check a numerical, they have given the ruling speed as 100 kmph and minimum speed as 80 kmph. So using the maximum value of super elevation is E is equal to 0.07 and F is equal to 0.5. With these conditions, substitute in the previous equation what we have looked. For ruling speed, to find out the ruling minimum radius, substitute V value as the ruling speed, and to find out R minimum or absolute minimum radius, we will substitute the minimum design speed of the highway in the expression. So with that we can find out what is the ruling gradient and the minimum gradient. Now the radius of the horizontal curve will be designed in such a way that the curve radius will be between these two values. So with this I'll conclude. In the next session we'll see how the vertical alignment will be done in the highways. Thank you.